Welcome to another course of continuing education for professional engineers. Session 9 of 10, LNG auxiliary systems. It's not all about LNG, and it's not all about bog. Without the auxiliary systems, the plant is dysfunctional. Many auxiliary systems are mission critical to delivering LNG to the vaporizers or to the production facility or to storage. Learning objectives of today are to understand the operation of most auxiliary systems at the LNG plant. The word most is used because not every LNG plant uses the same auxiliary systems. Some require unique specialized auxiliary systems, such as reverse osmosis, zero liquid discharge, and other unique systems. Learning objective of today will be to understand how critical it is to have every auxiliary system functional for safe, reliable LNG plant operation. And we want to understand how poor maintenance of auxiliary systems can make an LNG plant shut down and become totally unreliable. Auxiliary systems are needed to support LNG plant operations. Glycol cooling and heating systems needed to provide heat or to take away heat. Instrument air systems control all the instruments in the plant to move valves to various positions, open, closed, partially open. Plant air for maintenance personnel using pneumatic equipment. Plant water for maintenance personnel or operations personnel. Plant steam or hot oil systems to provide heat, maybe to reboilers, maybe to vaporizers, wherever heat is needed. Potable water, that's drinking water. Then there's fire water required for fire protection systems. Sanitary systems for the obvious, and water runoff systems. Certain water runoff systems will require oil separation units. Intrusion alarm systems for not only for buildings but for the plant perimeter as well. Flare or warm vent systems to remove excess gas from the plant, typically during an emergency. Fuel gas systems to supply fuel to emergency generators, to boilers, and to other pieces of gas consuming equipment. Electric supply for the entire plant, the whole network, all the switchgear, emergency generators, and uninterruptible power supplies. If you have an amine system or a boiler system, high pressure boiler system, you certainly want to have available demineralized water. You can either truck it in or have your own demineralized water system. Truck loading and unloading facilities for not only consumables in the plant, but you may want to truck out or truck in LNG itself. DCS, SIS, and firing gas systems. DCS is distributed control system, which allows you to control the entire plant from a central control room. And you could also use programmable logic controllers, but the newer plants, the larger plants, use DCS systems. SIS systems, which are safety integrated systems, look at the entire plant's grouping of sensors that are looking for anomalies. And in the event you have a hazardous condition, the SIS or system integrated system will take control of the plant and put it into a safe mode. Typically means no hydrocarbon flows other than to emergency equipment such as emergency generators and plants shutting down into a fail-safe condition. Emergency shutdown systems are a subset of your safety integrated system. It shuts the plant down or part of the plant down in case of an emergency. Drain systems and vent systems allow you to drain LNG or other liquids from your plant into a safe location and allows you to vent gas or other gases off of the system to a safe location. Typically, LNG boil-off gas go back to the tank, and other gases could be vented to the flare system. Pad gas, also called cover gas, is needed to protect large tanks that could see a vacuum. Vacuum can crush a tank. We want to make sure pad systems, also called cover gas systems, are available to protect those tanks. A typical tank that would require a pad gas coverage is your LNG storage tank. Another one might be your amine liquid storage tank, and also a recondenser is a large vessel that might require pad gas. Foundation heating system is needed if you have a large LNG tank that is placed on the ground. If it's on the ground, it'll be sucking heat out of the ground, and when it does that, the ground could freeze up and heave up and damage the tank. So you need to heat the foundation, and foundation heating systems are critically important. Fire protection systems are needed. There are many different types: deluge systems, dry chemical systems, etc., water spray systems, and so on. Nitrogen purge systems. Well, to have nitrogen purge, you need nitrogen. You may opt to produce that nitrogen on site, or you may opt to truck in that nitrogen, typically as liquid nitrogen, and store it on site. And then you vaporize it when needed. Offshore emergency escape systems needed if you have an offshore platform, and you may or may not opt to have an escape system, but the personnel need to be able to get off that facility quickly in an emergency if needed. Sometimes an escape system, which consists of a boat that jettisons from the offshore platform, is used. Offshore sewage systems. We have personnel offshore. You have sewage system needs. You need to either tote that material offshore or pipe it to onshore. Ammonia systems needed for emissions control. You need to store the ammonia and have the systems needed to vaporize that ammonia, spray it in, and apply it to your emission system to reduce NOx. Air separation units might be needed if you are going to be stabilizing vaporized LNG. Air separation units provide large quantities of nitrogen for send out for stabilization during send out. Zero liquid discharge systems separate solids from water, particularly salts from water, then allow you to reuse the water and then just ship out the salts that or the contaminants that have been removed from that water. And there are many, many other auxiliary systems that could be in your plant. Not everyone will be covered in this lesson. Let's discuss some of these auxiliary systems. Glycol cooling and heating systems. Typically, you use ethylene glycol mixture, or you could use propylene glycol mixture. The benefit of using propylene glycol is it's non-toxic and it's less concern about spillage and environmental issues. But ethylene glycol is a better conductor of heat, a better medium for heat transfer. So quite often, ethylene glycol will be used. Ethylene glycol is what's used in the car radiator of your automobile. Gas turbine oil coolers would typically use ethylene glycol to cool down the turbine oil in a heat exchanger, of course. Waste heat vaporizers would use ethylene glycol. Boil off and gas fuel heaters would use ethylene glycol. Vaporization systems often use ethylene glycol. Heating emergency vent gas systems, emergency generator cooling fluids. Glycol systems require pumps and heat exchangers. Glycol systems require glycol storage tanks and expansion tanks. If you have a glycol system, when it's hot, it expands. The glycol expands. You need a tank with a moving head level that allows you to take up that expansion, and then that same tank is used to reduce the amount of glycol when the glycol cools down and contracts. Instrument air is extremely important for your plant operation. The entire LNG plant is operated on instrument air. The instrument air moves valves and controls the instruments that allow the valves to open the amount that needs to be opened. Without instrument air, the plant cannot operate. Headers are often made of stainless steel to avoid corrosion and avoid debris traveling down into the instruments. It is critically important that your instrument air be at the correct pressure and capacity. It is also important to ensure that your instrument air has a low dew point, typically around minus 40 degrees Fahrenheit. It's typical for an instrument air compressor to be at least a two-stage compressor. Instrument air compressors are provided with dryers to bring the dew point down to that minus 40-degree Fahrenheit. These are typically pressure swing dryers, which means that you use dry instrument air to regenerate the desiccant in those dryers. Because these are pressure swing dryers, you need excess compressor capacity, which means that let's say you need 100 standard cubic foot per minute of air, you'll typically have a 200 standard cubic foot per minute of air compressor because about half of that air is used to regenerate your dryers. May not be half, but in that order of magnitude. The instrument air must be backed up. That's because it's such a critical component in the plant, meaning that you may have two, three, or four instrument air compressors all connected to the same header when only one might be needed, but you need that redundancy. Some places actually use nitrogen to back up their instrument air in addition to multiple compressors. Instrument air systems are typically double or triple backed up and typically can be supplied by the emergency generator. So if you lose electricity, you still need instrument air. So your emergency generator is built in place to provide electricity to your instrument air compressor. In some plants, AI is even backed up with nitrogen. This is not popular because of the concern of nitrogen entering into an enclosed space. Plant air is different than instrument air. Plant air is used for driving pneumatic tools for maintenance. Plant air does not need to be dried to as low a dew point as instrument air, but it needs to be dried to the point that you don't end up getting freeze-ups occurring. Instrument air is a separate header because you would not want to hook up a pneumatic tool to your instrument air line and drag the pressure down. So it's typically a separate header so you can hook up your pneumatic tool to a plant air header and it can see that sudden drop when the tool is turned on. It's not going to affect your instruments. Plant air is typically distributed around the plant using carbon steel pipes. You don't have the criticality of being concerned with any small amount of rust particles that might be carried down the plant. At least it's not as critical as with instrument air. Plant water. Plant water is typically used for maintenance, for cleaning, and for other water uses in the plant. Plant water is sometimes supplied by the plant's fire water system. To provide fire water system would be designed in such a way that you never draw down enough plant water so that you don't have the correct capacity for your fire water system, which means that you might have a tank and you're able to draw down that tank only to a certain level for plant use, always leaving the required amount for fire protection. Plant steam and or hot oil systems. Plant steam is typically provided by a boiler or a heat recovery system. Plant steam is used to operate steam lances to remove ice off of equipment. Plant steam is often used as saturated steam and is used as a heat source. There are many different requirements for heat sources in an LNG facilities. In particular, reboilers for a debutanizer in a production facility, regeneration gas to regenerate your mole sieve. Well, that regeneration gas has to be heated up to about 550 degrees. How do you get steam up, saturated steam up to 550 degrees Fahrenheit? You need to be around 1,000 psi absolute. Regen heat or regenerators or reclaimers on amine systems. Heat source for upstream of the fuel gas JT valve. Think about this. Your fuel gas comes off of the pipeline gas, which might be at a high pressure. If you're going to reduce that pressure, the gas coming out of the JT valve or the pressure reduction valve is going to be very cold. So it's typical to heat up the gas and then drop it in pressure across a JT valve. Potable water systems are for human use, typically drinks, sinks, and toilets. It's typically separate piping from any other piping systems, but they may have a single source or a single supply, and that could be the potable water slash fire water tank system. The fire water tank is a very large tank that would be on the facility, and the top part of it might be usable for drinkable water, and the bottom part would be for fire water, which means there's a tap about at some height in the tank that once the water gets below that point, the potable water can no longer draw from that tank. And the reason being that you have to have a minimum amount of water, that is a design minimum amount of water for the fire water system. Fire water is typically stored in a large water tank on site. Fire water is typically provided by both electric and diesel water pumps. You don't want to be in the middle of a electrical fire, not have electrical power, and not have a fire water system. So that's why it's backed up with a diesel water pump as well as an electrical pump. Typically, fire water is distributed through a system that is supplied by a jockey pump. A jockey pump is a small pump just to keep pressure on the system. When a demand is called for, let's say someone opens a hydrant, then the main pumps come into play. The main pumps would be the fire water pumps that supply the hydrant system that's within the plant. When the pressure drops even further, then the diesel pump would come on as a backup. But the fire water system is something that's ready and available 24 hours a day, 7 days a week. Fire water supplies monitors, deluge systems, bog dispersion systems. Those are sprays that would disperse when warm the bog, and high and low expansion foam systems. Sanitary systems and water runoff systems. I once heard that, oh, there's no sewers in an LNG facility. Well, if there's no sewers in an LNG facility, where does the fluid go when you flush the toilet? Uh, Obviously, there are sewers. However, these sewers need to be protected to make certain that in the event of an LNG spill, you would never get LNG into the sewer system. But there are sewer systems in LNG facilities. Sanitary systems are what's called black water sewer systems. Runoff water, typically called gray water, are systems that are needed to capture water runoff if it's raining out or if there's a spill of clear water or clean water in an area. Where water is contaminated, you need special containment vessels for that contaminated water. Where water runoff systems are in an area where oils may be present, the water is sent to an oil separator prior to disposal. LNG codes do not permit sewers or runoff water systems to be in locations where LNG, if spilled, would get into the sanitary or the runoff water system. Plant steam. Not all plants have auxiliary steam. Typically, large plants, such as export terminals, would have auxiliary steam. Large plants such as export terminals have auxiliary steam because they have large engine drive systems where the engine drives would have high exhaust heat. High exhaust heat produces steam through a HRSG, which is a heat recovery steam generator, and that steam is typically used for heat sources within the plant as well as often to drive a steam turbine and generate electricity. Steam is used in separation towers and regenerators as a heat source for reboilers. In order to heat reboilers to do the separation of zeotropic mixtures within a distillation tower, to heat reclaimers, to heat mold sieves that need regeneration. Now, regeneration heat is quite high. It's about 550 degrees Fahrenheit. So you need high pressure, high temperature steam. In order to have steam at 550 degrees Fahrenheit, it needs to be about 1000 psi absolute. Steam is also used in the plant for electric generation in some plants. In export terminals where there's a lot of heat recovery, the steam is used to extract heat from the large turbine exhaust and use that to drive the electric generation systems. Steam has also been used for heat tracing in large petrochemical plants. It's quite unusual to have it in an LNG plant, but it's one application for steam where electric heat tracing is not used. By prudency and by code requirements, intrusion alarm systems are required in LNG facilities. We would not want to have people who are unskilled or unknowledgeable to be around valves or any other equipment related to LNG. There are many types of intrusion alarm systems. Some of them use IR infrared beams, and the parameters to be protected have IR transmitters and receivers strategically placed around the plant. When a person breaks the beam, an alarm is sent to the control center. Closed circuit television is used to investigate, and if needed, then personnel would be sent out to further investigate. One negative about this type of system is that false alarms due to sun glare or bird flocks are often encountered. Vibration sensors on fences are also used. If anyone were to shake a fence or try to climb over a fence, the alarm would be sent to the central control system. And again, CCTV cameras would be used and plant personnel would be used as needed. Flare or warm vent systems. If there's excess gas in the plant that needs to be relieved to the atmosphere, it is typically sent to a flare where it is burned and therefore it's made safe. Once it's burned, it produces CO2 and water vapor. If it's going to be vented to the atmosphere, that would be a flammable gas, and therefore you want to warm the gas before it goes to the atmosphere so that it rises. Then typically a warm vent is at an elevated location, so it'll be typically at the top of a stack. The gas is warmed in order to make it buoyant. Bog itself is about minus 260 when it's produced, and even if it warms up to minus 150, it's just about buoyant at minus 150. Typically, the bog is heated up to at least minus 50 degrees Fahrenheit to make it buoyant enough to disperse in the atmosphere without it falling down to the grade level where people and equipment would be. Three methods are common for flaring or warm venting as follows. The use of a warm vent at an elevated location, the top of a vent stack, or at the top of a tank. Warm bog is vented directly to the atmosphere. The bog is warm to typically warmer than minus 50 degrees Fahrenheit before being released to the atmosphere. The use of elevated flares. Such flares are typically always showing with a flame on it. And in the event of an overpressurization or an emergency, the excess gas is sent to the flare. The negative about having a high level flare or a flare that's on a flare stack is that it's visible to the public. And anytime there is a difficulty, the public can get alarmed by seeing this large fire on top of the stack. The use of ground flares has become more popular in larger plants. Ground flares are at ground level and are typically surrounded by a high concrete wall. The ground flare pilots are always lit, and the staging valves are used to send gas to the many gas burners that are on the ground flare and the volume of, depending upon the amount of volume that needs to be flared. So if there may be 50 flares and maybe only 10 are in use during one flaring event. Maybe if the gas volume is more, might go to 20 flares. And there are different types of burners that are used. Some are used for low pressure gas, some for higher pressure gas. And each of these are tuned so that they give a clean, smokeless flare. Fuel gas systems are extremely important in a plant. Typically, fuel gas systems are natural gas taken off the pipeline. Well, if they're taken off the pipeline, they're at high pressure. You need to bring it down in pressure. And when it comes down in pressure, due to the JT effect, it gets colder. So you have to heat up the fuel gas before it is used. And you want to heat it up for several reasons. Gas coming off the pipeline has moisture in it. You don't want to have hydrates form, or you don't want to have freezing taking place in your control valve. Also, you want to make sure that the piping systems, which are typically carbon steel, do not operate below a temperature that is appropriate for that carbon steel. Carbon steel, when it gets too cold, becomes brittle and can fail. Boil-off gas may also be used as fuel gas. However, it also must be heated and then compressed before use. Diesel fuel is typically the fuel used for emergency fire pumps or for emergency generation needs. And typically, the reason why diesel fuel is used is that it can be stored on site. It is not dependent on your fuel gas system, because the fuel gas system could be compromised. That could be the actual emergency. Let's say there's a break or a fire in the fuel gas supply line. Well, that would be shut down, and then you would have no fire pumps and no electric generation capability. Fuel gas or bog is typically brought to a temperature of 40 degrees Fahrenheit before its utilization. That means that if it's at a much colder temperature, it needs to be heated. It is not uncommon for fuel gas distribution systems to be operated at a pressure of less than 200 psi absolute. Since natural gas does not act like an ideal gas, it needs to be heated before it is pressure dropped across a JT valve. Here I will explain a little bit about the JT effect that happens when you pressure drop gas across a JT valve. This is a partial view of a pH diagram, and it's in the gaseous stage at a relatively high pressure. If you take a look closely, you'll see at 1000 psi absolute, gas is at 40 degrees Fahrenheit. If I were to drop it across a JT valve down to 200 psi absolute, it would end up being minus 18 degrees Fahrenheit. Well, that's not acceptable. And you don't want to heat up the gas after the drop down, because at this temperature, ice would already have formed. So what's typically done is gas at 40 degrees Fahrenheit and 1000 psi absolute is heated up to approximately 85 degrees Fahrenheit and then pressure dropped. And where does it end up? 40 degrees Fahrenheit. So this is the heating that needs to be done here. This heating before you go through the pressure drop valve. Like with all petrochemical plants, electric supply is critical to the operation of the plant. Most small LNG plants use electric grid supplied electricity. For plants that are supplied by lines that are above ground on poles, it is a point of reliability concern. A car accident hitting a pole on a ice storm day that takes down the electric lines can render the plant unavailable. Larger plants generate their own electricity and are an electric island. They typically isolate themselves from the grid and rely totally on their own generation capabilities. Other plants have both grid supply electric and have enough electric generating capability to run all vaporization operations via their own electric generation. This is highly reliable, but very expensive way to operate. One of the things that's interesting is if you do have your own electric supply, I often ask the operator, have you ever tried operating the plant at maximum requirement using solely your electric generation capability? And quite often the answer I hear is no. So if you do have your own electric supply, I do recommend driving the plant to full capacity using that electric supply to see if everything performs the way it is designed to perform. Emergency power is essential for an LNG facility. It is necessary to run air compressors, necessary to run the fire protection system, and necessary to remove boil-off gas safely from the plant. All LNG plants must operate safely, and in order to do that, they must ensure that their emergency power systems are reliable. I was at one LNG facility where there were 7 emergency generators. After a rather severe earthquake, none of those generators were able to come online. Emergency electric generators are typically natural gas fired and typically supply only the critical loads, such as air compressors, control systems, fire and gas systems, heat to the fuel gas heaters, emergency lighting, intrusion alarms, communication systems, and other systems that are critical to the safe operation of the plant. Uninterruptible power supplies are critically important to the safe and reliable operation of an LNG facility. When power is lost, there is a short time lag between when the electricity is shut and the emergency generators come online. Critical computers and critical computerized control type systems cannot stay online if there is a momentary blip in the continuous supply of power. Many uninterruptible power supplies are located in different parts of the plant. Uninterruptible power supplies are supplied by battery banks, typically lead acid battery banks that require continuous maintenance. These are set up to instantaneously be the power supply to the critical equipment without any blip in the continuous power to the equipment or without any change in frequency to the equipment that is being supplied. Demineralized water. Demineralized water can be either made on site or be trucked in from another location. If an LNG plant is to operate with a large high-pressure steam boiler or with an amine system, they will need demineralized water. Demineralized water is water that has most of the mineral impurities removed from it. Demineralized water is made by reverse osmosis, which is a membrane technology, ion exchange, which is typically used in canisters to remove ion particles in a resin, nanofiltration, and distillation. Demineralized water is stored in tanks at the plant For smaller plants, demineralized water can be purchased and trucked into the plant, but for larger plants, it's wise to have a demineralization plant on site. Truck loading and unloading systems will be needed at your facility. If you are operating an MR system, that's a mixed refrigerant system, you will need to unload truckloads of your MR components unless you are distilling them on site. These may be ethane, propane, isopentane, etc. These will need to be demercurized and dehydrated before their use. If you have an amine system, you will need to truck in clean amine and truck out spent amine. If you do not make your own demineralized water, you will need to truck in demineralized water. If you are going to truck LNG, you'll certainly need LNG trucking capabilities. A distributed control system. Most plants can be operated by using a series of programmable logic controllers or by using a DCS system. A DCS system is a centralized supervision system with decentralized control. A DCS is designed to manage and control complex industrial processes by distributing control tasks across various subsystems. These subsystems communicate and coordinate with the central supervisor unit, but operate independently to ensure efficiency and reliable control. Improved process management. DCS facilitates real-time data collection, monitoring, and feedback control for processes in petrochemical plants. This ensures seamless operation and quick responses to change or disturbances, enhancing process stability and efficiency. Integrated safety and redundancy. DCS systems often come with a built-in safety protocols and redundancy to handle critical operations. This helps to maintain operations in case of failures or emergencies and continuously provides safe and functional plant operations. The Safety Integrated System is an enhanced safety and risk reduction system. A safety integrated system is designed to monitor and manage industrial processes to prevent accidents and reduce risk. It literally takes over the plant and puts it into a safe mode, such as no hydrocarbon flows in the plant other than to supply emergency generation. It acts as an additional safety layer by detecting hazardous conditions and initiating automatic actions, shutting down equipment, protecting personnel, protecting equipment, and protecting the environment. Compliance with safety standards is critical for an SIS system to be designed correctly. SIS is engineered to meet strict industry standards, such as the IEC 61508 and the IEC 61511 codes, ensuring that petrochemical plants adhere to global safety standard regulations. These systems are rigorously tested and validated to provide reliability and performance in critical situations. There is redundancy and fail-safe in their design. SIS components are designed with redundancy and fail-safe features, ensuring that they remain operational even in case of component failures. This ensures continuous protection and reduces the probability of system failures, crucial for maintaining the safety of a hazardous environment like a petrochemical plant. Emergency shutdown systems. Emergency shutdowns usually occur as an action from the SIS. An emergency shutdown is a series of automated actions that occur when an SIS or a PLC program logic controller triggers an emergency shutdown. An ESD renders all parts or part of the plant in a fail-safe mode. It shuts down the flow of all flammable fluids except for fuel supplying emergency needs, such as fuel for emergency generators or fuel for the flare pilots. ESDs can be localized to a single piece of equipment, localized to a specific process, or it could be the entire plant. The bog system, LNG system, air separation plant, these would be localized systems. An entire plant would be obviously an entire plant shutdown. ESDs can be for the total process plant, typically for a major hazard like a fire. An ESD can also be for the total process plant, which includes the utility plant. This is typically only in the event of a fire within the utility plant. You would not want to shut down your air compressors unless there is a fire in the utility plant where the air compressors are located. Programmable logic control systems. These are automated for essential processes. Programmable logic controllers, PLCs, are used in petrochemical plants to automate and control a wide range of processes, including fluid handling, chemical mixing, and equipment operation. Their reliability and real-time response capabilities make them ideal for managing complex sequences and high-speed operations within the plant. Adaptability and customizations. PLCs offer flexibility in programming, allowing them to be tailored to specific control requirements of different processes. This adaptability enables engineers to modify and optimize plant operations as needed, supporting efficiency and continuous improvement in the plant. Integration with other systems. PLCs can be integrated with other control systems such as the DCS and the SIS to provide comprehensive control and monitoring network. This interoperability helps in enhancing process management, data collection, and overall plant safety. Fire and gas systems. There are multiple systems in a plant to sense hazards. The main one is the fire and gas system. Its main function is detection and monitoring. A fire and gas system in a petrochemical plant is designed to continuously monitor the facility for fire outbreaks, gas leaks, and other hazardous conditions. It uses a range of sensors, for instance, flame detectors, heat sensors, gas detectors, to detect potential threats at an early stage, ensuring prompt action. Automatic safety response. Once a fire or gas hazard is detected, the fire and gas system initiates an automatic response to mitigate the risk. This is typically done through the SIS system. This may include activating alarms, triggering fire suppression systems, initiating plant shutdown procedures, and isolating the affected area to protect personnel and equipment. Integration with plant safety systems. The fire and gas system is the eyes and ear of the safety integrated system, allowing the safety integrated system to do shutdowns and to make the plant safe. The fire and gas system is often integrated with other safety mechanisms, such as the safety integrated system, and to enhance the overall plant safety. This interconnection approach ensures coordinated responses and provides comprehensive protection against fire and gas-related incidents. Relief valve and rupture disc systems. These are safety devices used to prevent over and under pressure. Many different types of relief valves and rupture discs are used in the plant. There are spring-loaded pop-type pressure relief valves, pilot-operated pressure relief valves, balanced bellows pressure relief valves, and vacuum relief valves. Thermal expansion safety valves, that's TESV, are used where a liquid could be trapped between two valves or locked in a vessel. As the liquid expands and the pressure rises, the TESV relieves that pressure. LNG typically relieves to an LNG header and is sent back to the LNG tank. Bog typically relieves to a bog header, which is connected to the LNG tank. The exception to this would be the relief valves on top of an LNG tank. These relieve directly to the atmosphere. Rupture discs typically vent to the atmosphere, where rupture discs or relief valves discharge glycol or glycol water. It is typically contained in an impound area. Ambient temperature natural gas is typically vented to the atmosphere. Drain and vent systems. During normal and emergency operations, it is often necessary to vent gas or to drain liquid from a system, a pump, etc. And this would be sent either to the heated vent or the flare system. During normal and emergency operation, it is often necessary to drain liquid hydrocarbons to vent the system, which would be sent to a liquid holding drum. If the liquid is cryogenic, it would be heated and then the vapors would be warmed and vented or flared. If the liquid is warm, it would be sent to atmospheric holding tanks, such as dirty amine. Pad or cover gas systems. Pad gas is sometimes called cover gas. They are the very same thing. Pad gas is typically taken off the fuel gas system. Pad gas is a gas that is added to large tanks to prevent them from experiencing a negative pressure. Such tanks are typically protected by a vacuum relief valve. However, the cover gas system is set to provide cover gas to the tank before the vacuum relief valve activates. This avoids bringing air into the tank. It is common for large tanks and recondensers to be connected to a cover gas system. Foundation heating systems. LNG tanks that are in direct contact with the ground require a foundation heating system to avoid ice lenses from heaving up under the tank structure. LNG pumps that are submerged in the ground require ground heating systems around them to avoid ice lenses from heaving the pump up out of the ground. LNG tank heating systems are typically accomplished by having conduits traverse the bottom of the tank. These conduits typically hold heating wires. In early years, the thermostat for these systems were controlled by an on-off thermostat. Newer systems use modulating voltage control. Fire protection systems. There are two main independent fire protection systems at an LNG facility, a wet system and a dry system. Other firefighting equipment include brush fire trucks, such as four-wheel drive vehicles with 500-gallon tanks of water on them to put out brush fires, dry chemical trucks, dry chemical systems, deluge systems, wet pipe sprinkler systems, CO2 systems typically used in turbine generator encasements, handheld, portable, and wheeled fire extinguishers are placed throughout the plant. FM 200 or similar protection systems are used for control houses and for substation protection. FM 200 is only one of many types of gases that inhibit the combustion process. It is used in places where water would not be used because the water would damage the computer systems in place. Nitrogen systems. Nitrogen is used to purge out pipes and vessels as a component of mixed refrigerant, to blanket tanks' contents to assure that non-explosive environments exist in the tank, to allow the capture of seal leakage for rotating equipment, such as compressors, to monitor electric seals, maintaining nitrogen pressure on those seals, to maintain electric boxes as explosion proof. Nitrogen can be trucked in as liquid nitrogen. Nitrogen can be made via a nitrogen generator. Nitrogen can be made by way of using an air separation unit. This is typical if it is needed in large quantities, such as for stabilizing send-out. Offshore emergency escape pods. This is for totally offshore plants or import-export LNG plants. And not all plants have these, but some plants opt to have these depending upon the offshore configuration. In some offshore LNG operations, emergency escape systems are in use. These are for rapid evacuation of offshore personnel. These are totally enclosed boats that have sealed doors and the ability to be ejected into the water. These boats are motorized so they can be driven away from the event that caused the need to evacuate. Ammonia systems are typically used with catalysts and are used for control of exhaust emissions. They're used for the reduction of NOx components in the exhaust. The ammonia reacts with the NOx within a narrow band of temperature to produce N2, nitrogen, and H2O. Typically, it's used on exhaust from turbines. However, in many cases, it's also used for the exhaust of combustion appliances such as heaters, boilers, and in particular for submerged combustion vaporizers. This typically is used with a selective reduction catalyst and dilution air. Air separation units are used to produce large quantities of nitrogen where stabilization is required or where ship purging is required. Air is compressed and cooled and dehydrated. The air is brought down to a liquid state via an expansion process. Liquid air is distilled into nitrogen and oxygen in two towers. The liquid nitrogen is stored. The cooling from the liquid oxygen is used to generate more liquid nitrogen. Oxygen-rich off-gas is exhausted to the atmosphere. Care must be taken, as oxygen-rich gas can make a flame accelerate very rapidly. Care must be taken to not allow any hydrocarbons to enter the inlet air to an air separation unit. Zero liquid discharge systems are typically used to reclaim water and make it reusable. Water containing solids, typically salts, is pH adjusted and then passed through filters to remove suspended solids. Through evaporation and condensation in the brine evaporator, the concentration of impurities in the remaining liquid increases as the evaporated water is reclaimed for reusable water. In the final steps, a supersaturated solution is stirred in a crystallizer, where solid salts drop out of solution and are collected while the evaporated water is reclaimed to be reusable water. Crystallized solids are pressed, dried, and sent out for disposal. Let's talk for a moment about auxiliary systems reliability. A loss of any one of the highlighted auxiliary systems will shut down the plant. You lose your glycol water heating system, plant is shut down. Instrument air, plant is shut down. Plant steam or hot oil system to provide heat to various subsystems, shut down the plant. Fire water systems, well, you should not be running the plant while your fire water systems are down, so that would shut down your plant. Flare or warm vent system, again, those are safety systems that are needed for safe plant operation. You should not be operating your plant without those systems being functional. Certainly, a fuel gas system will not work without your plant, without the heat that's needed for certain processes. Electrical supply, well, that's a no-brainer. No electricity, no plant operations. DCS, SIS, fire and gas systems, other hazard alarm systems, emergency shutdown systems, drain and vent systems, relief valve systems, nitrogen purge systems. All of these are essential to operating the plant. The other systems are required but not necessarily essential. For instance, the ammonia system is for emissions requirements, and you may end up having to be in violation of emissions for a short period of time, but the plant can still operate. Your offshore sewage system, you may have to bring out porta potties, but the ability to operate your plant is not necessarily shut down. But there are certain systems that you must. If I had to pick the one system that stands out as being the most important, I'd have to say it's a toss-up between the instrument air and the computer systems that control the plant, because control is key, and control is done by both the instrument air as well as the computerized systems that control the plant. So what we've done in this course is review auxiliary systems. We did not cover every auxiliary system, but we covered the ones that I consider to be key to most plants. And you can see that the auxiliary systems play an important role in maintaining the LNG plant safe and reliable. Unfortunately, because they are auxiliary systems, quite often they do not get the maintenance attention that the LNG and bog systems get. So you need to keep in mind that the auxiliary system is as important as the LNG and bog systems. They must be kept functional and highly reliable.